Welcome students to my ninth lecture of Control System 2. So today we are going to discuss about the relation between state space representation and transfer function, that is canonical realizations of state space representation. So last lecture we have discussed if a state space representation is given, then how we will find the transfer function from that. Also we have understood that for a given system the state space representation is not unique. We can create different model or state space representation for a given particular system, but the input output relation, that is the transfer function, is unique. So today we are going to discuss that if the transfer function is given, then out of that how we can find out some of the standard representation of state space, because we know that for a given transfer function the state space realization for a given system can vary, means we can create infinite number of realizations, but our aim is to discuss some of the canonical or standard realization out of that, and then you can ask that what is the motivation to to find out certain canonical realization or standard realizations, because this realization later we will see that some of the realization will be helpful to analyze the system behavior. Means suppose for a given system which is represented in state space, and if we want to find out the system response for a given input, if we able to represent that system in a certain representation, it will be very easy to calculate the time response of the system. And also some of the model you will find that in this lecture we are going to discuss that it will be useful to analyze the stability of the system. If the system is particularly represented in that canonical form, it will be easy for us to determine the stability of the system. And some forms or some standard form you will find that it will be helpful in the design, when we want to design the controller or when we want to design the observer. If the system is represented in that particular standard or canonical form, then it will be easy for us to design. So these are the things we will discuss when the time will come, but at this moment only you will know that how to create certain standard realization if the transfer function of a system is given. So as a beginning you can see that state variable model for LTI system, we are concentrating on linear time invariant system and mostly the single input single output system. So if the system is represented in state space, that is x dot t equal to a into xt plus b into ut, yt equal to c into xt plus d into ut. In the last lecture we have discussed that how for a MIMO system we can find out the transfer function matrix using the relation 2. And if we will assume that d equal to 0 and we are dealing with a CISO system, then instead of getting a transfer function matrix, we will get a scalar transfer function which is represented by relation 4. So now the canonical realization of the state space, what we are going to discuss, that is the controller canonical form, observer canonical form, observability canonical form, controllability canonical form, diagonal form, and Jordan canonical form. And here in the last lecture we have seen that if a state space model is given, how to compute the transfer function. Now in this lecture we will do the reverse thing, that is if the transfer function is given, then out of that how we can find out these canonical realizations. And one thing you should remember that now we cannot show you the use of this realization, but when the time will come, when we will discuss the time response as well as when we will discuss the stability of the stability of the system which is represented in state space, and when we will discuss about the controller design and observer design, definitely we will recall this canonical realization. But at this moment you have to learn that if a transfer function is given, out of that how we can find out the canonical realizations, and time being we will concentrate on these standard realization or canonical realizations. So first we will start with the controller canonical form. That is, suppose a transfer function for a nth order CISO system is given by g is equal to 1 by s to the power n, a1 s to the power n minus 1, like that, plus an. So this is the representation of a nth order system which is LTI as well as CISO. Now if we write the differential equation involved with this transfer function, then we have to cross multiply, assuming y and u are the output and input of the system, and then we will take the inverse Laplace transform to get the differential equation. So the differential equation with the nth order system is represented by this. Now this a1, a2, an minus 1 and an are constant, and most importantly you can see that this input term u2 ut does not involve any derivative terms, so it is only ut. So now no u dot or u double dot terms are there. So if this kind of systems are present, if this kind of systems are to be modeled using state space, and that is in the controller canonical form, then how we are going to do that one. So now we know that if a transfer function is given or a differential equation is given, then first we have to assume the state variables. So now for the controller canonical form, to construct the controller canonical form, we have to assume, or we have to define the state variable in this fashion, that we have to assume x1 equal to y, then we will write x1 dot, that is y dot equal to x2, then x2 dot is equal to y double dot, that is x3, then xn minus 1 dot is the 1 minus 1th derivative of y, which is defined as xn, and then ultimately xn dot, which is nth derivative of y can be written from this differential equation, that is minus an x1 minus an minus x2 minus a1 xn plus u. So now we will we want to represent this set of differential equation in block diagram, and from there we will try to find out the state space representation. So let us try to find out the block diagram representation of this state and output equations, which is defined in equation number 5. Now you see, if we want to construct the xn dot, that is y of nth derivative, then we require the information of x1. What is your x1? So x1 is y, and what is your x2? x2 is y dot. So we require the information of y dot, y double dot, then y that is y n minus 1th derivative. So now, and then for a block diagram, I told already that we have to start with the input and we have to end with input u. Sorry, we have to start with input u and we have to end with output y. So now you see that the block diagram representation is like this. So now here clearly we can see that we have started with u, that is input, and we are going to end with the output y. And now to construct the y, the nth derivative of y, we require that we require the y, then we require the y dot, okay, and then we require y double dot, fine, and then we require xn minus 1. So xn minus 1 dot is what? Now xn minus 1 dot, if you see here in this expression, xn minus 1 dot is the n minus 1th derivative of n minus 1th derivative of n minus 1. Okay, so we can see that this will be the y of n minus 1th derivative. Okay, so this way we can find out the block diagram representation, because now if we want to implement the y of nth derivative, we require what? We require an x1, okay, minus an x1. You see minus, if you see the the expression, we can, you see, minus an x1, that is actually y, then minus an minus 1 x2, okay. So this minus an minus 1 into y dot. So in this way we have represented, and now the hint is that the output of the integrator will be the state variable. So that's why all the outputs of the integrators are marked as a state variable. So output of the integrator is x1. This output of the integrator we have given the name x2, and then like that, this will be the x of n minus 1, already it is defined, then it will be x of n, okay, and then is this basically is representing xn dot, okay. So now once it is defined, then you can transform this set of differential equation 5 in terms of state equation, and now the nth order CISO system can be represented in vector matrix notation like this. And try to remember that, and this form is known as controller canonical form, where A, B and C matrices having a specific form. And now you can see that the last row are the coefficients of the transfer function in a reverse order. Now you see, if you see the transfer function, that is s to the power n a n s minus 1 a2 s minus n minus 2, then a n minus 1 into s plus a n, and exactly the in the reverse order it is in the last row of the A matrix. And the B matrix have a form, all the elements will be 0, only the last element of the B matrix will be 1, and C matrix the first element is 1 and all other element will be 0. If you able to represent any system in this form, then we will call it you have represented the system in controller canonical form. So let us try with an example. Suppose one example has been given, that is gs ys by rs is equal to 24 by s cube plus 9s square plus 20x plus 24. Now we have to represent this system in a differential equation. So now a differential equation, associated differential equation, we can represent it by 12, and next step will be to represent it using block diagram. So if we represent it block diagram, so RT into 24, then y triple dot is required minus 24 yt, minus 26 y dot t, and minus 9 of y double dot t. So now how we will, from y triple dot, how we will get y double dot? Now if we place the integrator, then from y double dot how we will get y dot? By integrating, and y dot to y by another integration. And now to represent the y triple dot equation, then we have to feedback it with a proper coefficient, that is 9, 26 and 24. And next step, you can define the state variables, and obvious choice of the state variables will be the output of the integrator. So if we will assume that this is x1 and this is x2 and this is x3, and definitely this is representing x3 dot, then you can find out the state equation from this block diagram. And the state equations will be x1 dot equal to x2, x2 dot equal to x3, and x3 dot will be minus 24 x1 minus 26 x2 minus 9 into x3 plus 24 into r of t. And now if we represent it in state space, then the A, B, C matrices will be like this. So now this is the representation of any system in controller canonical form, where you will find that the transfer function do not involve, or the differential equation do not involve any derivative of the input. Now the second case we will discuss about the controller canonical form, where we will see that derivative of inputs are involved. But before that, another important thing we want to tell that, you see here we have assumed that the output of the integrator is x1, x2, x3. If somebody will go in the reverse way, suppose if somebody will assume that this is x3 and this is x2 and this is x1 and this is x1 dot, then what will be the system representation? And that has been shown in the next slide. That is, if it is like this, means suppose this is x3, then this is x2 and this is x1 and this is x1 dot, then the same system what we have taken as an example, you are finding that the state equations will be represented by 15 and that vector matrix notation will be with 16. And here you can see that here the first row are representing the coefficients of the characteristics polynomial in a order, that is here you can see that minus a1, minus a2 and minus a3. Okay, so in this way it is there, you can see minus. Okay, so if you assume that this is SQ plus A1 S square plus A2S plus A3, then you can see that it is minus A1 minus A2 minus A3. This also could be a representation in controller canonical form. And here why we are correlating with the transfer function with the state space model, because some occasion will come that if the transfer function is given to you directly, you have to write what will be the controller canonical form by identifying the coefficients of the characteristics polynomial. Okay, and where the 24 is sitting at the B matrix, this can be written in this way also. You can take this is 1 and this is 24 into UT, that also can be written, and the output equation you can see that it is 0, 0, 1. So this also a representation of controller canonical form for a given transfer function if you just change the order of the assumption of the state variable in the block diagram. Now as I told you that if now some situation will come if the differential equation involves with the derivative of the input. Suppose we are taking an example of a third order differential equation where you can see that the inputs at the right hand side we have the derivative of the input, that is u dot and u double dot. Now, if this kind of differential equation is given, then we can find out the transfer function. So, the transfer function representation will be like this: b1 s square plus b2s plus b3 by sq plus a1 s square plus a2s plus a3. So now here you can see that the numerator polynomial, the degree of the numerator polynomial is lesser than the degree of the denominator polynomial. So now in this situation, how we can find out the controller canonical form? At this point, I want to mention that though we have taken the example of a third order system to understand it easily, but the same thing can be extended for the nth order system also. So once you will understand for a third order model, then it can be easily extended for the nth order model also. Means any order of the system is given to you, you can find out the controller canonical form. So now if this is the transfer function, then how we are going to find out the controller canonical form? So now what we will do that we will introduce a third variable, that is zeta s. Means the same equation, means that is ys by us is written in this way: ys by zeta s into zeta s by us. Okay, means you can think in this way that we have a relation something like this, that is we have the relation that is ys by us. Now what we have done, we have assumed a internal variable. Okay, so that is ys by ys here zeta s, and then we have the u of s. So if we can write the block diagram in this way, then the zeta s by us can it be written 1 by sq plus a1 s square plus a2s plus a3. And if you see the equation 17, just now we have discussed that if there is no input derivative terms are associated like 17, how to represent this fact or this transfer function using controller canonical form. And another part you can see, that is ys by zeta s, that is b1 s square plus b2s plus b3. Okay, so now we will write the time domain representation of equation number 17. So then we can write that zeta triple dot plus a1 zeta double dot plus a2 zeta dot plus a3 into zeta equal to ut, and from here we can write what will be the zeta triple dot. And equation from the equation 18 we can write the output yt is beta 1 zeta double dot plus b1 zeta double dot b2 into zeta dot plus b3 into zeta t. Now we will use these two equations to represent it in block diagram, and from the block diagram it will be easy for us to define the state variables, because the hint is that the output of the integrator we will assume as a state variable. Let us try to implement this. So now we have to implement zeta triple dot, and here I have missed one term, that is it will be plus of ut. That's that term I have missed. So now we have to start with the input and we have to implement zeta triple dot. For that we require zeta dot double dot, zeta dot and zeta. So how we will get that one? In this way we will start ut with the ut. Now we want to represent zeta triple dot, so we want zeta double dot. So you integrate it, you will get zeta double dot. Then again you integrate it, you will get zeta dot. And again if you integrate, these are the integration. So again if you integrate, then you will get zeta. And then with the zeta double dot, if we will multiply a1 and if we add it with minus a2 zeta dot minus a3 zeta, we can construct zeta double dot. And once we will have the zeta dot and zeta double dot, easily we can implement the output equation also, because output equation is b1 zeta double dot. So you see b1 zeta double dot plus b2 zeta dot plus b3 into zeta, and we are getting the output. And now we will define the state variables very easily, and the output of the integrator will be the state variables. So suppose this is the x1 and this is the x2 and this is the x3, and now we will write the state equation and the output equation. So if we will write the state equation, then we are finding that the set of state equation will be x1 dot is equal to x2, x2 dot equal to x3, and x3 dot is equal to minus a3 x1 minus a2 x2 minus a1 x3 plus u, and the output equation will be b3 into x1 plus b2 into x2 plus b1 into x3. And now from here it will be very easy to find out the controller canonical form. And now very interesting to see with respect to transfer function where the which elements are sitting. So now you see this is b3 b2 b1, they are coming into the output equation. How they are written? The b3 b2 b1 and a3 a2 a1, okay, they are the coefficient of the s are sitting at the A matrix, okay, A matrix, and the coefficient of the U is sitting at the B matrix at the last. So this is 1 into U. Now here we have assumed that this matrix is called AC, controllability, or the controller canonical form, that A matrix is represented by AC, this is BC, and this is C of C. So in this way, so here again I am telling that here the two cases we have considered to represent the system in controller canonical form. So first we have assumed that the transfer function where the numerator having no term, only it having constant term, means it means that in a differential equation we do not have any derivative of input, And another case we have considered, the differential equation have derivative of inputs. In these two cases, how we can find out the controller canonical form. Now the thing, the same thing we have shown here with an example. Suppose gs equal to cs by rs is given, and this transfer function has to be represented in controller canonical form. So now, as I told you, that we can write this transfer function in this way with the help of a intermediate variable. Here in intermediate variable we have written x1s. It means that we have written, that is, cs by rs in this way, that is cs by x1 of s into x1 of s by rs. And then from there we have tried to represent it in a block diagram, and after the block diagram we have given the name of the state variables as the output of the integrator, that is x1 x2 x3, and from there we have found out the state equation and output equation, that is represented in vector matrix notation. And you can see that 271, that is b3 b3 b2 b1 are came into the output equation, and the coefficients of the s in a reverse order came into the A matrix, and the coefficient u came into the B matrix. So we can easily verify how the transfer function given in the form that is represented in equation 21 can be represented in controller canonical form. So now next we are going to discuss about the observer canonical form. Okay, so now again we have taken the third order differential equation where it involves the derivative of inputs. So now the same differential equation can be represented using transfer function gs equal to like this. So now we have to represent this one in an observer canonical form. So same system we want to represent in a standard form, that is observer canonical form. So for this, to represent this system in this particular form, we have to assume the state variable in a particular way. Then only we can have the observer canonical form. And here is the procedure. So the third order differential equation is written in this way, that is y triple dot is equal to minus a1 y double dot minus a2 y dot a3 into y plus b3 into u b2 into u dot plus b1 into u double dot. Now from this equation, if I want to find out what is yt, then how we can write? Now yt can be written if we will do the 3-time integration. So if in this side, if we will do the 3-time integration, then we'll get yt. So now the 3-time integration has to be done in the right hand side also. So if we will integrate, suppose this term 3 times, if we will integrate y double dot t 3 times, so what we will get from here? We will get integration y of t. Okay, so here I have not shown the dt term, so only to understand how many times it is integrated. That is actually our intention to know. So now the same with the same concept, we can write the first one is the first integration of yt. Okay, so like that other terms are written, and most interestingly this a3 into yt, so you have to integrate this yt 3 times. Fine. So like that the input terms are also written. Now what we have done, we have found out the like order of integration. So suppose it is single time integrated and this is also single time integrated, so these terms we have written together, so that results in the next equation. You see, minus a1 single integration of yt plus b1 single integration of ut. So now if we want to implement the yt from starting with the ut, so these are the variables are related with these equations. So first equation you try to understand, that minus a1 into yt, okay, plus b1 into ut, that has to be integrated one time, and then same quantity yt and ut is multiplied with different coefficient minus a2 and b2, and it has to be integrated two times, and the same quantity or same variable yt and ut has to be integrated three times, and it is multiplied with minus a3. And here I think I have missed one term, that is here it will be b3. Okay, here it will be b3. So now we will try to represent this equation y of t, the last equation we have written, in terms of block diagram, and from the block diagram we will try to define the state variables. Okay, so now if we want to do, then how we can represent it, now we will start with ut. You see, we have started with ut, and the end must be with yt. Now we are trying to implement the first term, so minus a1 into yt. So minus, so you see minus a1, so this is the minus a1 into yt, and it has to be added with b1 into ut. So here we are getting the addition, and then it has to be integrated, okay, to get the yt, because this is only the single term we have implemented for the construction of yt. So only this term we have integrated. Now you see the same quantity yt and ut has to be integrated two times, but it is multiplied with different coefficient a2 and minus a2 and b2. So what we have done, so to implement it, the second term, so then again we have feedbacked with yt into minus a2, which has been added with b2 into ut, and then it is integrated again. Again this quantity is passed through one integrator, and output of the integrator is added, because these two terms, which two terms, these are the two terms, this term and these terms are added, and this yt and ut will be doubled, it is double integrated, and that is also done. You see, this quantity is going to pass through another integrator placed here. So similarly, the third term also we can have, that is minus a3 into yt. So minus a3 into yt we have done, minus plus b3 into ut, and this term has to be integrated three times, so it has been added here with an adder. So this term is now integrated three times to get the yt. So in this way, you see, we have generated the three terms and then added to get the yt. Now it will be very easy for us to define the state variable. Suppose this output of the integrator we have taken x3, okay, and this output of the integrator we have taken x2, and this output of the integrator we have taken x1. So definitely it will be x1 dot, it will be x2 dot, and this will be x3 dot, and from here we will try to write the state equation and the output equation. So from the block diagram we can see that output y is equal to x3, and x1 dot, suppose x1 dot if I want to write that, we can see that minus a1 into x3, okay, plus b1 into u. So plus sorry, yes, x1 dot, so x1 dot, sorry, x1 dot, so we are representing the x1 dot, sorry, we are representing the x1 dot. So x1 dot will be minus a3 into x3 plus b3 into ut, correct? Okay, now if we want to represent the next that is x2 dot, so what will be the x2 dot? Now x2 dot will be the x1 plus b2 into ut minus a2 into x3, okay. So now that has been represented in the x2 dot, okay, and similarly we can find out the x3 dot from the block diagram. So once we will get the x1 dot, x2 dot, x3 dot, then easily we can find out the observer canonical form, which is represented in equation number 24. Now most interesting thing is that how the A matrix look like. So if it is an observer canonical form, the particular form will be look like this, that is minus a3 minus a2 minus 1 is the last column, okay, and b3 b2 b1 are sitting in the B matrix, and the C matrix will be 0 0 1, and we have named it A0, B0 and C0 respectively, okay. And the similar way here I want to mention that similar way, if we will assume that this is x1 and this is x2 and this is x3, then also you will get another model for the, means in that case your A matrix is going to be changed and B matrix and C matrix is going to be changed. That also will be the observer canonical form, okay. But now most interesting thing is that we want to find out the relation between the controller canonical form and observer canonical form, and the relation exists. So if this is the representation of the observer canonical form, correspondingly if we see the controller canonical form, then you will find that a relation exists. So let us see the form which is represented in terms of a1 a2 a3, where it is, let me see, here I think, yes, here, okay. So now if you see that a0 means, sorry, AO, which is in the observer canonical form, is the transpose of ACT, okay. And if you see the B matrix of the observer, it is the transpose of C matrix of the controller canonical form, and the C matrix of the observer is the transpose of B matrix of the controller canonical form. So this way you can remember, means one form if you get, other form easily can be generated by using this relation, okay. So which is represented by here. So if this is the CCF, means controller canonical form, and this is the OCF, then the relation between A0 means A observer, B observer and C observer will be related with the AC, CC and BC like this. So this you can remember because sometimes if you get one form, that is controller canonical form, the observer canonical form can be easily derived, or if you have the observer canonical form, then controller canonical form can be derived using this relation. So now we will discuss about the observability canonical form. So now the observability canonical form has been defined with the state space representation by equation number 28. So here only noticeable thing is that B observer is defined with the variable beta1, beta2, beta3, okay. But A matrix and B matrix for the observability canonical form already represented in terms of the coefficients of the polynomials in the transfer function, but only, or we can say that they are expressed in the parameters of the system, okay. What are the parameters of the system? Like if a differential equations are given, the coefficients of the differential terms are the parameters of the system. So now A matrix and C matrix is represented, matrices are represented with the parameters of the system except the B matrix. So now here our job will be to find out what is beta 1, beta 2 and beta 3 in terms of A1, A2, A3, B1, B2, B3. So that is the what we have to do. So now we will define that y equal to x1 for the observability canonical form. Then y dot is x1 dot, and from the equation 28 we can see that equation 28 x1 dot is equal to x2 plus beta 1 into u, and then y double dot, that is we can write that is x2 dot plus beta 1 into u dot, And how we will write x2 dot? X2 dot we can write from the state space equation, that is basically x3 plus beta 2 into u. So here x3 plus beta 2 into u plus beta 1 u dot. So similarly we can write the y dot, y double dot, which is x3 dot plus beta 2 into u dot plus beta 1 into u double dot, and x3 dot can be written from the state space representation, and the equation will be like this. And now we will recall what is our objective. Objective is to find out the beta 1, beta 2, beta 3 in terms of the A's and B's. They are the parameters of the system. A's and B's means small a, means this in terms of A1, A2, A3 and B1, B2, B3. So we want to calculate, or we want to express beta 1, beta 2, beta 3. So to do that one, we will recall our original differential equation from which we are making the transfer function, the state space model. So this is the third order differential equation, and if you substitute the y double dot, y triple dot, y double dot and y dot and yt from this expression, so y dot, y double dot and y triple dot, you just substitute at the left hand side of the equation. Okay, then after some cancellation you will find that you can group the terms like this: the coefficient of u, the coefficient of u dot and coefficient of u. Okay, uh, here I did a mistake. I think it will be beta 3 a1 beta 2 plus a2 into beta u, and this will be beta 1 u double dot. So it will be u double dot. Okay, so now only u double dot. So now only you have to compare with the like powers of derivative of u. So if you compare u double dot with this, so we are getting beta 1 equal to b1, and then beta 2 we are getting, that is from here, if you compare this and this, we are getting b2 minus a1 beta 1, and already beta 1 we got that it is b1, so we can replace that, and beta 3 we can calculate with this expression. So in this way we can represent, or we can calculate what is beta 1, beta 2, beta 3 in terms of the system parameters, and then we can have the representation of the system in state space, what it is specified in equation number 28. So now the same equation, state equation, what it is represented in this equation number 28 can be represented in the block diagram like this. Here these are the integrator, three integrators are there, and the output of the integrators are assumed to be the state variable. Okay. And now from here it is very easy to represent the observability, means controllability canonical form, because once you have the observability canonical form, you can derive the controllability canonical form by the relation which is exhibited here, that the controllability matrix A will be the transpose of A observability matrix, and B controllability matrix will be equal to C observability transpose, and C controllability will be the B observability transpose. So in this way you can represent the controllability canonical form for a given observability canonical form. So now here I want to stop. So in this lecture we have seen that four canonical representations, how to derive or how to find it from the states, from the transfer function. We have seen they are the controller canonical form, observer canonical form, controllability canonical form, and observability canonical form. So next class we will discuss about other two representation, that is diagonal form and the Jordan canonical form. But here one thing you try to remember, that in this moment I cannot show you the uses of this model, but as the course will progress, definitely we will use these models as when required. Thank you.